Okay, year 11s. This is the second part for chapter 2G linear models. In this video, we're going to look at two examples and see how we actually implement the linear relations in construct a model. Now, during the class, I mentioned that the importance of recognizing key parameters. Okay, so just to recall, what are the key parameters that you have to use? We have the y equals mx plus c, and this is our general linear equations. So there are a few of the parameters we have to identify, and first of all is the two variables here. Right? You have the x and y variable. So the x variable, we call them the explanatory variable, or EV. The y, we call them the response variable, or the RV. So these two is you need to firstly determine from the passage. So normally we say the response variable, it is the result from the explanatory variable, or we can say explanatory variable explains the response variable. After identify these two, the next step is to be able to identify these two key parameters. Okay, so the m, we know the m is the gradient. In linear applications, they often relate to rate. Okay, so I put gradient here. It often relates to rate. So for example, speed is a rate as it represents the distance per every unit of time traveled. Or the unit cost. Yeah, for example, the amount of money you have to pay per unit of quantity of an item. Yeah, so those are rate. This one, okay, it is the fixed charge, fixed amount. Okay, always say the vertical intercept. Okay, so bear in mind with these four parameters that we have to identify first. Okay, now let's look at the part A. Before we start to identify the key parameters, let's construct a little diagram to better understand the scenario. So now you have a train. Okay, you have a train. So you move at the speed of 50 kilometers per hour in a straight line away from a town. So here you start at the town. D1 is measuring along with the direction, yeah, along with the direction that the train travels, yeah. Okay, so we know that the distance equals to speed times the time, yeah, time it took. So in this case, we can use this information to try to construct a linear model. Firstly, let's try to identify the two key parameters, which is the explanatory variable and the response variable. So here I have the distance and the time t in hours. Yeah. Now, since we've trying to identify which one is the explanatory and which one is the response, we have two directions. Either we can say the time is spent, the train spent on traveling, that will explain the distance the train will travel. Or the other way, or we say, is the distance that the train travel explains the time it spent. Clearly, it's the first one, the first one. So this is the RV, that's the response variable, and then this is EV, that's the explanatory variable. Okay, so we can start by writing D1, it is equal to something with t, yeah, something with t. Now here we see that the speed, we have identified that the speed, which is technically a rate term, and that is the gradient. Okay, so that's a 50 kilometers per hour, which is also here. That's a 50. That is the time, and that is d1. Yeah. And from looking at the diagram, the distance at the beginning was 0. Okay, when t is 0, the distance d1 it should equal to 0 as well. Therefore, there's no vertical intercept. Also, we're going to say something about the time here. So we know that the time is measured from the time and travel away from the time. So we know that the t cannot be negative, right? So t has to be greater than or equal to 0. It doesn't specifically says where the train stops. So for this point, the t has no limitations of choosing that any positive real number. Let's look at the part B. The part B says a train has stopped at a siding 80 kilometers from the town and then moves 40 kilometers per hour in a straight line away from the siding towards the town. So in this case, the diagrams it is a bit different. So here we got the town and here we got a siding. So we note that the distance between the town and the siding is 80 kilometers. And then the train is actually move from this side, okay, is moving from this side that travels towards the town, yeah, it travel towards the town. So has this speed that is 40 kilometers per hour. Okay, and then we have the time. Now, in this case, what is d2? The d2 is the distance that is measured from the town, okay, after leaving the siding. So the d2 it is measured this way. Okay, d2 is measured this way. Let's construct a little equation. So we know that from looking at here, we know that the d2 plus the distance the train travel should equals to 80. Yeah, should equals to 80 kilometers because the total distance between the town and the siding is 80 kilometers. The more distance the train travel, the less distance that the d2 will be measured. So in this case, again, we firstly identify the two variables here. So clearly the d2 here again is going to be the response variable, yeah, and the time. So the time here is going to be the explanatory variable. Okay, so before we continue, it's based on these little equations, okay, we're going to transpose to make the d2 the subject, okay, meaning make the d2 sit on one side. Therefore, this distance of the train have to be moved to the other side by subtracting it, which you get negative distance of the train plus 80. Okay, and then how can we find out the distance of the train? Well, the distance of the train it is equal to 40t, yeah, 40t. Therefore, d2 it is equal to negative 40t plus 80. Okay, don't forget we have a negative originally, so you should have a negative there. Okay, we know that the t has a limitation. We're going to work out what the values of t that we can choose. So first of all, we can say that the t can be 0, right? When t was 0, d2 reached to maximum, which is 80 kilometers, which makes sense here, right? While the train is still at the siding, the total distance, well, the d2 is actually equal to the distance between the town and the siding. When t equals to a number that we don't know, that we also know that d2 will reach to 0, right? The d2 will reach to 0 as the train has arrived at the town. So now we need to find out what's going to be the time that makes d2 0. And then you got 0 equals to negative 40t plus 80. Okay, so then you move the negative 40t, you got 40t equals to 80, and then t is equal to 2. Okay, so we know that the maximum time here that you can choose is going to be 2 hours here, right? Because when t equals to 2 hours, the train will arrive at the time. It's going to be the end of this diagram, right? So the train arrived at the time, and then d2 becomes 0. All right, so we have done the first two parts, and let's look at the part C, okay? Let's look at the part C. So for part C, that it says on a separate set of axes, so we're going to sketch the graph of d1 against and t, which is between 0 to 4, and then d2 against the t, and state the gradient of each graph. So I have already done these two graphs, which I would like to just quickly go through each of them. This one on the left, it is the d1. So we know that it starts at 0, yeah, which when distance d1 is also 0, when t equals 0. Now, because here the question says for the D1 graph, they give us the maximum t that you can choose is 4 hours, which means we have to substitute when t equals 4 hours, D1 that is reaching 200 kilometers. Okay, so that's why we have our line segment here. You have the both endpoints. So as for the second question, we have already set up values of t's be able to choose. So we know that when t was 0, you get the d2 reach to maximum, which is 80. And when t equals to 2, d2 reach to minimum, which is 0. You can't have a negative d2, right? By looking at the gradient for the first one, which is straightforward, that it's the speed of the train that is 50. As for the gradient for the second diagram, okay, now just be aware, although 40 is the rate, but because in this equation you see that the numerals or the coefficient in front of the variable, the explanatory variable t, is negative 40, which means the gradient itself is not 40 but negative 40. Okay, so this is example 1. Now let's look at the second example here. So again, I'll give you 2 minutes to read the passage. You may pause the video. Part A, it says find a formula of the sum registered, which is the total amount of money, in terms of the number of notes. Okay, so we know that they already tells us the two variables. Okay, now we're going to determine which one is the response variable, which one is the explanatory variable. Okay, remember we're using this statement. Does the number of notes explains how much, or is how much that explain how many notes? Well, technically it should be the first one, right? So this is going to be the explanatory variable. Here is going to be the response variable. And we also know that the gradient is going to be the coefficient of the explanatory variable, yeah? So we know that the gradient between 2 points has the formula m equals to y2 minus y1 over x2 minus x1, yeah? Instead of having a y, we have the c, yeah? So we have a c2 minus c1 over, and then instead of x, we have n2 minus n1. Take a look which one is going to be c2 or which one is going to be c1. It doesn't really matter, okay? So I just tend to choose the bigger number. So let's say this is c2, this is c1, and then the corresponding number of nodes is going to be n2, okay? And 1. You must make sure that they are corresponding variables that you put it in, you substitute into the formula, okay? So in this case, you got C2, which is $975, minus C1, that is $775, over N2, that is $160, minus N1, that is $120, okay? And then you got 200 over 40, which is 5, okay? So we found out the rate is 5. Basically, it tells you all the notes that they've counted for, they are $5 note. So we found out the gradient equals to 5. We still need to find out the potentially vertical intercept here, okay? So what we're going to do, we're going to construct an equation. Here is assume initially the sum was, let's say, B, okay? So the sum was B dollars. Okay, now we can construct the equation. We can say C, it is equal to, we have the gradient already found out, 5 N plus B, okay? You have 2 points to substitute. You can either substitute the N2 C2 or you substitute the N1 C1, okay? So here I'm going to substitute the smaller number. So we're going to substitute N equals 120, C equals to 775. Okay, so now you have 775 equals to 5 times 120 plus B. 5 times 120 equals to 600. And then we can easily find out that the B is going to be $175. Yeah, so initially they should have a $175 have already been counted. Let's rewrite the rule. We have a C equals to 5N plus 175. Okay, now sort of answer the part B as well. So part B says, was there a sum already on the register when count begins? Yes. Okay, of course it's a yes, otherwise you won't see the vertical intercept. Yeah, and for part C, if so, how much? That's $175. Okay, so these are the two examples we're using linear relations to construct a model. Again, if you got any questions, make sure you come and ask me or come to messenger message support. Thank you for watching, guys. Looking forward to see you in the next video.